Hi everyone, and welcome to our second daily revision booster. Just like the previous one, we're going to go through a topic in biology, a topic in chemistry and a topic in physics in order to help you obviously prepare for any of these upcoming assessments. First thing though, let's have a look at our daily formula, which today is acceleration. So acceleration in meters per second squared is the change in speed in meters per second divided by the time in seconds. This is again one you need to memorize, so make sure you put it on a flashcard and learn it. For today's Biology Blast, we're going to be having a look at natural selection. So we're jumping into one of those topics from B5, the fifth biology topic, which is going to be on that paper too. Hopefully we do remember one of these key facts, that when we talk about organisms and their evolution, they do so through this process of natural selection, which was suggested by good old Charles Darwin. What we need to know are the different stages, because quite frequently this kind of question can be worth multiple marks. So you could be looking at 3, 4 or even up to 6 marks for just a natural selection question. So knowing each of these steps, really important. Step 1 then is variation. What we need to say here is that organisms show variation within a given species, and as we get mutations occurring, we get more variation, because obviously mutations in genes could lead to a new characteristic. New characteristics are obviously variations within our species. Best example of that, as you can see at the bottom, there's Darwin's finches with all their different beak lengths as a reminder. Step 2 of natural selection is what we term survival of the fittest. Now, foundation papers, you tend to get a 1 mark if you've not got anything else for the phrase survival of the fittest, but it's a good way to remind you of what stage 2 is. The best way to do this though is to actually give the 2 sentences underneath. The organisms that are best adapted to their environment will survive, whereas those who are not well adapted will die. So rather than just writing survival of the fittest, what you need to do is saying after, obviously, the fact that within a species we do have variation, those that are best adapted to their environment will survive, those who are not well adapted will die. Step 3 is the reproduction stage. So this is where those that are best adapted will survive long enough to reproduce, which leads really nicely on to step 4, which is all about passing on that advantage. So the genes from those parents are then passed on to the offspring, and that means the offspring are likely to have the same advantageous characteristic as their parents. Step 5 is the repeat stage. It's worth remembering that when we're talking about evolution, it's not a case of it happens once that we get one mutation, they survive, they pass on their genes, and what do you know, we have a whole new species. No, it takes many of these to occur over a long period of time. So what we find is that process of stages 1 to 4 being repeated over and over many generations can lead to the development of a new species. So that is natural selection. We start off with variation, so we've got variation within a species. Step 2 is going to be those that are best adapted will survive, whereas those that are not well adapted will die. Step 3, those that are best adapted survive long enough to pass on their features because they can reproduce. Step 4, their genes, use that word genes, are passed on to the offspring, which means they will also have the advantageous characteristic. Step 5, it's repeated over many generations. And that's it. That is natural selection. Quick reminder of today's daily formula. Acceleration in meters per second squared is the change in speed in meters per second divided by the time in seconds. For today's chemistry check, we're going to be going through a couple of the different variables that can affect the rate of a reaction. So this is one of our C5 topics, the fifth chemistry unit, on paper 2 for chemistry again. Now, the first one is temperature. And the key thing with temperature is when we increase the temperature, the rate of reaction increases. That's the pattern. Increasing temperature increases the rate of reaction. The why, the explanation, is because when we increase the temperature, the particles gain kinetic energy. When they've got more kinetic energy, they move faster, and then they have more frequent successful collisions. And what we're going to find as we go through these, this phrase here, more frequent successful collisions, this is going to be like your best friend, your go-to phrase, what you're going to parrot back to me every time I sort of ask you to explain why we get this change in the rate of reaction. Then more frequent successful collisions is kind of a go-to phrase. When it's temperature, you write that down, you're getting marks. So temperature, increase the rate, because the particles gain kinetic energy, moving faster, more frequent successful collisions. Second factor we're going to look at is concentration then. So when we're talking about concentration, it's quite simply how much solute is dissolved in the solvent. If we've got a more concentrated solution, there's a greater mass of solute dissolved in the solvent. When we consider the impact of concentration on rate, then increasing the concentration increases the rate of reaction. The reason for this is that in the higher concentrations, then the particles are what we call more crowded. So that means they will have more frequent collisions. Successful not needed here, because the success of a collision is all to do with has it reached activation energy, and just changing the concentration won't affect that. But more frequent collisions, go-to phrase for rate of reaction. And just to show you at the bottom, we've got those little pictures. So this is a low concentration on the left, because we've only got two of our little solvents there in the red. And then on the right, we have a high concentration. So we've got lots of the little red particles. They're more crowded, they're more likely to collide with the blue. Therefore, increased rate of reaction. There will be more frequent collisions. One thing we do need to bear in mind is why a reaction will come to a stop or come to an end. And the reason for that is because the limiting reactant has been used up. So anytime you get a question that sort of says, why does this reaction come to a stop, or why does the graph level off? It's because the limiting reactant has been used up. The limiting reactant, quite simply, is the reactant that is used up first in a reaction. And as we've said, the way we can spot that on a graph is because it plateaus. And what we mean by that is a rate of reaction graph generally will have an increase, but then it levels off to a horizontal line. This plateau, that means it's no longer reacting. So at the point that it levels off over here, that is where the limiting reactant was used up. The third factor we'll just consider today is pressure. This is for gases, okay? We're not talking about liquids or solids. Pressure applies to gases. So if we increase the pressure, then we have a faster rate of reaction again. The reason, because the particles become more crowded, so they collide more frequently. So you'll notice we have these two phrases for both pressure and concentration. So more crowded particles and more frequent collisions. And you can see the little picture at the bottom there just showing you low pressure on the left, more space, so the particles are less likely to collide with each other. On the right, higher pressure, the particles are more crowded, therefore will collide more frequently. Another quick reminder of today's daily formula: acceleration in meters per second squared is the change in speed in meters per second divided by the time in seconds. Today's physics prep, we're looking at magnets and the magnetic fields that surround them. Hopefully, going back to the work we did in Key Stage 3, these two statements are very familiar to us. If we have two bar magnets that we place next to each other, then we get different things occurring depending on which poles face each other. If we have two like poles, so by like poles what we're referring to there is a north pole facing a north pole or a south pole facing a south pole, then they will repel, they push away from each other. Whereas if we have opposite poles, so a north pole facing a south pole, they attract, so they're going to pull towards each other. Surrounding our magnets, we have these things called field lines, and the field lines represent magnetic flux. So what we will actually see are these pictures down at the bottom. So if we look at the one on the left first of all, this is a single bar magnet, and they can ask you to draw these field lines. So make sure you know these pictures. For a single bar magnet, you will notice there's lines that go from the north and curve round to the south. So you can see that this part here, closer to the middle, they do go right the way round. Okay, so they literally touch the bar magnet on the north end and they touch on the south end. When we get towards the end, so these kind of areas, then what we can see is they kind of go, but they'd be going on a much wider arc, so we don't draw a whole thing there. And then this one here at the very end just is a nice straight line pointing outwards. You will get 1 mark usually for drawing the actual pattern and a second mark for the all-important arrowheads. And they always go from north to south. Okay, so remember the arrowheads, north to south. Please go careful when you're drawing these, because what we don't want to see on any of your diagrams is some kind of, you draw some of these terrible sort of like things like this that's, I don't know, it just looks like it's gone hairy. Or when we're actually drawing these lines coming around here, you've got this one here and then your next one for some reason, rather than going around the outside of it, it then randomly comes and crosses inside. Please draw this neatly, because you will lose marks for that kind of thing. If we then look at the picture on the right, we have 2 bar magnets. So north pole facing a south pole. What we can see is generally it's about the same, but between the two you can see that the field lines go from north to south. So what we have is those field lines joining between the 2 poles of the magnet. So just remember the difference there between a single bar magnet and 2 bar magnets next to each other. And it's worth remembering that when we're talking about these field lines, the more of them there are, then the greater the magnetic field strength will be. If we think about why the magnets will either repel or attract, it's all to do with the movement in the direction that makes the field lines shorten. So if we've got north to south, remember those field lines are passing from north to south. So they're going to attract because those are going to pull together to shorten those field lines on the left. Whereas on the right here, we've got like poles, a north pole facing a north pole. So what we're going to find is the magnet is basically going to have to turn one of them through 180 degrees in order to have that connection to shorten those field lines. Hence, they repel. We have 2 types of magnet we need to know about: permanent magnets and induced magnets. Permanent magnets are ones that are magnetic even when other magnets or a current is removed. So they are just magnets all the time. An induced magnet is only magnetic when it's in contact with another magnetic material, or it's around a current carrying wire that then generates a magnetic field of its own. So an induced magnet is a magnet we produce when a magnetic material is placed in a magnetic field. And the key thing about induced magnets is when you take them out of that magnetic field, they may not remain magnetic. So there'll be a magnet when they're in the magnetic field and not a magnet when they're not in the magnetic field. We can explain that using this thing called the domain model. So what the domain model says is that magnets are made up of these small magnetic regions called domains. In a permanent magnet, those domains are all lined up, so it's magnetic. In a magnetic material that's not currently magnetized, They have those regions, those domains, but they are not lined up. When we place it in a magnetic field, they do line up. Therefore, it becomes magnetic. When we then take it out of the magnetic field, the domains can go back to their original direction, no longer lined up, no longer magnetic. If obviously they were to remain lined up, then it stays magnetic. Hopefully you found today's little daily booster useful to you, and don't forget to join us again tomorrow for booster number 3.